The second representative application of computation is data mining. As you know, the term mining itself implies finding a mineral deposit, such as digging for and discovering diamonds. Data mining is to find the diamond class log from massive amounts of data. Fields to which data mining has been applied are many. In business, for marketing and trend analysis, in industry, for process planning and various logistics. In biology and medical science, DNA analysis became a standard tool for various new findings, and protein-related data has been used for drug discovery, and so on. There are again good examples that a new and clear view is provided by computation. And seems like one can discover something interesting so long as there are enough data on a given subject. Oh, you might have heard something like this somewhere. Let's recall it. Maybe this gives us a hint to understand how to conduct data mining. Yes, when we discussed the cryptanalysis of Caesar cipher, we have said as long as you have enough English text to go by, you will find the most frequent character that would correspond to the letter E. Once you discover that, you will be able to tell how far the characters were shifted. That is the target key K for the cryptanalysis. How could we find the most frequent character? Yes, by counting. By counting the occurrences of each character, we could find the one that appears most. Now, this key K is in fact the law how a message is encrypted. So finding the key is, in other words, mining an important law from the data, that is a ciphertext. And counting is essential for this task. In general, counting is a fundamental method for data mining. Let me give you an example of data mining. Suppose we are given a database of 8,000 mushrooms, like this. About half of them are edible, that is, non-poisonous mushrooms, and the other half are poisonous mushrooms. For each mushroom, this database records 20 features, such as its shape, the color of its cap, type of spots on its cap, and so on. Each line here corresponds one mushroom, and the values of each line represent the characteristics of the mushroom on those features. For example, the values of this column are the types of the spot on each mushroom's cap. Then our task is to find out a rule that would allow one to look at the mushroom and determine whether the mushroom is edible or poisonous. This is our data mining task. Here, a basic method is again counting. We count the number of mushrooms whose spot type is Y and edible or poisonous. Then we know, at least in the database, for example, that among all mushrooms with a spot type Y, 94% of them are poisonous and 6% are edible. In this way, we will be able to get the correlation data between each feature type and being edible or poisonous. Then, based on these correlation data, we will be able to find a good rule like this for characterizing poisonous mushrooms. After basic counting, the derivation of this type of rule may not be so easy. Yes, in fact, finding a perfect rule is an NP problem, and it is sometimes the case that this task is hardest among all NP problems. Well, it is not so difficult to see that finding a rule is an NP problem. This is because once you are given a rule, you can check its correctness easily by going through the database. and unfortunately, finding a perfect rule sometimes becomes very hard to compute. So if we believe P is not equal to NP, then there is no universal and efficient method for solving all data mining tasks. But we wish to solve a given data mining problem and find a rule anyway. Here, statistics and algorithm design would become important. Well, in our real life, compromise is important when facing something that cannot be overcome as it is. We may change our goal from the perfect rule to reasonably good rule. Here, the meaning of reasonably good becomes important, which is a subject of statistics. Also, we don't need a perfect algorithm that works in all cases. In computer science, through investigation of hard NP problems, several methods have been developed for designing such algorithms that work approximately or partially. Combining these investigations, researchers have obtained several useful pseudo-algorithms for data mining. This research subfield or techniques obtained there is usually called machine learning. I would again point out here that supercomputers are crucial for conducting some of the heavy and very important computations in data mining. For the last application area of computation, let me talk about AI, that is, artificial intelligence. This is also an important area. However, this is not an easy thing to explain. The reason for this is twofold. First, in this day and age, many types of processes that computers are involved in are called AI. For this reason, it is hard to distinguish what is really AI and what is not. So in this setting, let me explain what I think represents AI. By the way, when people say AI, there are two meanings. One is AI as a research area, and another is AI as a system. Hereafter, I will try to say AI area and AI system to distinguish them. When we discuss AI as an application area of computation, the input and output become crucial. This is the second complication. Up till now, we have been considering what is happening in a computer is computation. But when we discuss AI systems, discussing how to provide input and how to present its output after the computation becomes vital. The conventional method of computations considered of inputting data from a keyboard and displaying the computational results on the screen or the monitor, or perhaps on a printer. However, when it comes to AI systems, there are many more input and output methods or modes. They may be exactly as what we humans do. Input from the eyes, from ears, nose, touch, or tongue. On the other hand, the output may in fact consist of using a mouth to speak or to move its feet, hands, or fingers. The relationship to these non-computational areas becomes quite important too, which makes things more complicated. Again, let us consider all these from the viewpoint of computation. If we think this way, the computational part that becomes the nucleus, when it comes down to it, is the part that is common to data mining. That is, computational and also statistical techniques studied in machine learning. They are at the very core of the both AI area and data mining. So if we consider one aspect of AI area, and if we consider its computational key technologies, AI area has the same root with data mining. However, there is a major difference between data mining and AI area, which may be from their goals. The goal of data mining is to discover useful rules. On the other hand, the goal of AI area is to create a system that performs like a human on a given task, or an expert, or even more than a human expert, like a Superman or Superwoman. Due to the differences in their goals, there are intrinsic differences. First, inputs to AI systems are coming from various sources, from devices similar to eyes, nose, ears, and so on. Sometimes they are much more precise or sensitive than our original input devices. But sometimes data from those input devices contain various noise. In a nutshell, the input data is not uniform at all. In fact, it is quite diverse. The diversity can be seen also in output. Maybe output is more diverse. In fact, what it is expected could not be called as an output. Rather, it is regarded as performance or behavior. Furthermore, in many cases, we don't even know the correct answer. For example, if the task is to drive safely as human, then how can we specify the safe driving? Or if the task is to make a poem that moves many people, then more concretely, what sort of poem that the machine, that is AI system, should produce? Like these examples, it is often the case that the goal or the correct answer cannot be specified clearly. This may be even a character of AI area. Then, this question naturally arises. How can we verify whether the created AI systems satisfy our purpose? Or in more general, how can we accept AI systems? The first question is indeed what AI researchers have been investigating as a first priority subject. Standard engineering type tests are, of course, necessary, but besides these, we need to develop more efficient and robust methods, including new type of tests using computer simulation. For the second question, much wider discussion and investigations involving the society are necessary. Actually, whenever we had some new technology in the past, our human society tried to adjust itself to make best use of it by introducing new social systems, including new regulations. Maybe we need new social science for discussing our future society with AI systems. Unfortunately or fortunately, the speed of change is so fast. So here again, we had better be efficient. And for this, again, computation can be of some help. In near future, I believe we will have what we can call computational social science that investigates the society from the viewpoint of computation and with the help of computation. With this, I would like to close the appendix lectures. Though I had to simplify my explanations, and sometimes they were rather crude, I hope I could explain typical research activities of computer science and also some of the representative examples on how computations are applied to you. I also hope you enjoy the whole course. Based on what you have studied in this course, I encourage all of you to dive into the various worlds of computation. Then I believe you will experience new and exciting computations. When you reach that new place, I believe that you will find that the basics that you have learned here are going to be very useful. With this, I will end the lecture on the Introduction to Computer Science. Thank you very much.